Good morning, friends. We have so far made a first attempt to develop perturbed equation of motion, and we are more focusing on longitudinal motion. When I say longitudinal motion, we all understand we are talking about a motion restrained into vertical plane, and there are three motions which we are considering. One is motion along x, translation motion, motion along z, which is plunging motion, and motion about y-axis, which is pitching motion. These three motions we are considering to restrict our discussion for longitudinal case with an assumption that the disturbances are small, so that there are no influences of longitudinal disturbance on lateral or directional case, right? And if I recall, we had equation of motion of this form, m u dot plus q w minus r v equal to f x a minus m g sin theta. This is one of the equations, and along z direction the equation was m w dot plus p v minus q u is equal to f z a plus m g cos theta cos phi, and the pitching equation is I y q dot plus r q I x minus I z plus I x z p square minus r square equal to m. Now we need to understand the right hand side. What is fxa? You see, fxa is actually equal to fx aerodynamic plus fx because of thrust. Similarly, fza is fz aerodynamic plus fz because of thrust, and m is nothing but pitching moment. This is nothing but pitching moment. To make our life simple, we'll make an assumption that whatever treatment I do for fxa, it assumes that as if fxt is not there, or whatever treatment I do for fx arrow, similar treatment could be made for fxt. We'll give some examples as we mature, but at this point we'll assume that for our fxa, it is basically fx arrow, right? With clear-cut understanding, if I understand how to handle fx arrow, fx because of aerodynamics, I know how to handle fx because of thrust also, right? We'll understand this in clear terms as we develop the equations, perturbed equations of motion. So this is basically longitudinal perturbed equation of motion, what we are looking for. And what was the approach? The approach was we write u, total u after disturbance is introduced is u1 plus small u, v is v1 plus small v, w, w1 plus small w, like p, also p1 plus small p, and like this, with a clear-cut understanding that we are talking about small perturbation. So I can write it like this, that is total velocity after disturbance being introduced along u v directions can be represented by linearly by adding the perturbed quantity to the steady state quantity. And this is strictly valid for small perturbation. And as long as this is valid, our approach is valid. If the disturbance is such, I cannot write like this, then our analysis is not valid. Okay? And what we did, we substituted this here and tried to cancel out few equations and derived finally, if I am not mistaken, we got equation of the form. For Fx we got, Fx is aerodynamic. And where from this Fx is coming? Just for your clarity, we got this is as Fxa1 plus Fx. So what is Fx? Fx was perturbed aerodynamic forces. Please understand, this Fx ideally will have perturbed aerodynamic force plus perturbed thrust force, right? But we are now understanding how to handle this, assuming this to be only aerodynamic, and for thrust we can easily extend this analysis and get the correct expressions. So once we do that, we got equation something like this: Fx minus mg theta cos theta 1 equal to mu dot. And please understand, here we have also used the concept of, if you see my last lecture, I have used the concept of stability axis. And what was stability axis? Suppose this is the airplane, and at steady state, let's say this is the velocity vector v, total velocity v. And now I align my x-axis xs such that the x-axis points to a total velocity v, and accordingly z also get tilted. And the advantage of using stability axis is that now w1, the w component at steady state is 0, because now the x is along the total velocity in the vertical plane, right? Okay. So this was one equation we derived, and then second equation also we had Fz minus mg theta sin theta 1 equal to m w dot minus q u1. This is another equation which is in z direction, and for pitching moment equation it was very straightforward. You could see again I use this equation for pitching moment, and I write q as q1 plus small q, r as r1 plus small r, like that. Theta is theta 1 plus small theta, and all these things if I do here in this equation, then I will get equation of the form m equal to iy q dot. So these three are my perturbed equations of motion longitudinal case. Okay, longitudinal case. This is just to revise whatever you have done the last lecture. Let us carefully see what are these equations. These are longitudinal perturbed equation of motion. Meaning thereby, what we are saying, what is this small u? Small u is the perturbed velocity along local x direction. What is Fx? Fx is the perturbed aerodynamic forces. What is Fz? Perturbed aerodynamic force along the local z direction. And this is the perturbed aerodynamic moment about y direction. And to see whether the aircraft is dynamically stable or not, I need to track the values of u, q, and w, right? And from that variation, we should be able to comment whether the aircraft is dynamically stable or not. That is why we have developed these equations of motion. But the question is, do I know how Fx, Fz, and m are changing? Because you understand, if the airplane is at steady state like this, and if there is a disturbance, then this angle of attack will change, pitch rate will change, right? So the perturbed aerodynamic forces, which comes because of lift and drag, also will change. So I need to explicitly know how this Fx, Fz, and m are changing. To know that, first I must know mathematically what are those motion variables, what are those control variables on which fx, fz and m largely depend. Okay? So we'll write that fx, it goes without saying we are only taking aerodynamic forces, because we know that if I can handle aerodynamic forces mathematically, that technique if I understand, I can extend it for thrust also, right? So we'll write it like the df ax by du into u plus df ax by d alpha into alpha plus df ax by dq into q plus df ax by d alpha dot into alpha dot plus df ax by d delta E into delta E. Where from we have got all this? How suddenly we are writing like this? Because we understand this fx is function of u alpha alpha dot q delta E. This is the first model assumption. And this is more or less true for small disturbances, right? Okay. We know now fx is function of u alpha alpha dot q and delta E. So we can easily expand fx using the partial derivative concept for a linear system. But we need to know that these derivatives are evaluated at steady state. Physically, what does it mean? I mean, suppose I am flying this machine like this, and there is a change in alpha, right? So I need to find out what is that gradient in sense of partial derivative dfx by d alpha at steady state. I evaluate that and then multiply with perturbed quantities and add it up, because we are talking about linear system. So I should be able to model fx as a function of u alpha alpha dot q delta E. So the next question comes, do I know how to evaluate this? How to evaluate this? If I know how to evaluate this, I should be able to make our life simpler, because now I will be knowing how fx explicitly is changing with motion variables and control variables. So let us take these derivatives one by one and try to see how it can be evaluated. But before I do that, we also write similar way fz as df az. You can write it yourself, du into u plus df az by d alpha into alpha plus df az by dq into q plus df az by d alpha dot into alpha dot plus df az by d delta E into delta E. Similarly, you have become expert. The perturbed pitching moment can be expressed as d ma by du into u plus d ma by d alpha into alpha plus d ma by dq into q plus d ma by d alpha dot into alpha dot plus d ma by d delta E into delta E. So mechanical. Once I know this, I write this, and once I want to write this, I also assume that fz is also function of these variables. Similarly, once I write this, I also assume that m is also function of u alpha alpha dot q and delta E. So this is the first part. Okay. Now let us take one by one and see what are the little bit of mathematical manipulation required to get some meaningful answer. Let's say we take fx. Fx is what? d fax by du into u plus d fax by d alpha into alpha plus d fax by dq into q plus df ax by d alpha dot into alpha dot plus df ax by d delta E into delta E. Let us take first this case. Let us also see what is the dimension of alpha. Alpha is angle, it's dimensionless, right? Radian, right? Q, it is radian per second. Alpha dot, radian per second. Delta E is dimensionless. U, meter per second. Now, it creates a complicated mathematical inconveniences. What we want to do, we want to express fx using motion variable in a non-dimensional form. So, what we will do, we will write fx as dfx ax by d u by u1 into u by u1. We are trying to non-dimensionalize the motion variable or control variable. Anyway, control variable is non-dimensional. So, what we have done, this motion variable perturbed u was meter per second. So, we have divided by u1 the velocity at steady state along x direction, and the derivative we have changed at dfx by du by u1. So, it is all the same, we are not changing the actual nature. Similarly, here we write dfax by d alpha. Alpha is already dimensionless, nothing to be done. But here when I come for q, I find q is a dimensional quantity. So, we do it like this. Which you are familiar, from q radian per second, we are changing it to qc by 2 u1, which is dimensionless. And similarly, we do it here, df ax by d alpha dot c by 2 u1 into alpha dot c by 2 u1. Then here, I remain same, and I don't do anything for the last term. That is already dimensionless. Angle is dimensionless. Okay, so what does this tell us? That yes, we agree, now these are all dimensionless, but now you need to calculate these derivatives defined in this fashion at steady state. Okay. So now our approach will be, how do I find this derivative dfx by du by u1? We will be referring this as u derivative. This will be referring at alpha derivative. This will refer to as q derivatives. This will refer to as alpha dot derivative. This will be delta E derivatives, correct? So, if you understand that, it is not difficult for you to write fz as, it is not difficult for you to write fz as d faz by du by u1 into u by u1 plus d faz by d alpha into alpha plus df az by dq c by 2 u1 plus df az by d alpha dot c by 2 u1 plus df az by d delta E into delta E. No problem. Okay. What is the catch point? Catch point is, don't forget, all these derivatives, partial derivatives, I need to evaluate at steady state. Similarly, now you can write m as dm by du by u1 into u by u1 plus dm by d alpha into alpha plus dm by dq c by 2 u1 into qc by 2 u1 plus dm by d alpha dot c by 2 u1 into alpha dot c by 2 u1 plus dm by d delta E into delta E. It goes without saying that we have to again evaluate these derivatives, partial derivatives, at steady state. All of this. Once we know how to evaluate this partial derivative, I will know explicit form on which fx, fz and m depend. That is our motivation. Okay? And how we are going to categorize them for our own understanding, we will say dfx by u, du by u1, dfz by du by u1, dm by du by u1, they will be referred to as u derivatives. So, there are u derivatives, which is like dfx by du by u1, dfaz by du by u1, then dm by du by u1. There are alpha derivatives, which will be dfax by d alpha, df az by d alpha, dm by d alpha. Similarly, q derivatives will be dfax by dq c by 2u1, then dfaz by dq c by 2u1 and dm by dq c by 2u1. We will have alpha dot derivatives and delta E derivatives. So, alpha dot derivatives will be dfax by d alpha dot c by 2u1, then dfaz by d alpha dot c by 2u1 and dm by d alpha dot c by 2u1. They are alpha dot derivatives, and we have delta E derivatives. They will be dfax by d delta E, similarly dfaz by d delta E, and similarly dm by d delta E. Please understand, when I write delta E, I am talking about elevator. If the perturbations are coming because of any other control surfaces which are affecting longitudinal motion, let us say flap deflections, then the delta E has to be replaced by delta F or a flap. This is to give you the basic idea. There may be multi-control longitudinal control. So, you have to go on adding those influences, right. And another thing, what about these derivatives? We need to evaluate these derivatives at steady state, and that is the catch point. Okay. Why we are doing all these things? Let us again understand. We want to solve those three equations which represents longitudinal perturbed equation of motion, where we need to know what is explicitly the expression for fx, fz and m. If I somehow calculate these derivatives based on the geometry of the airplane, based on the flight conditions, based on the environmental condition, if I can find it out, then I know explicitly how fx, fz and m are changing with alpha q, alpha dot, delta E. Those I will plug in the equations of motion and try to solve it to see what is the behavior of u, alpha q, etc., those perturbed quantities, to comment whether the aircraft is dynamically stable or not. Right. Next lecture we will be finding out. Thank you.